Okay, let's go ahead and continue on with problem number 3. Again, I'm going to try and move a little bit quicker this time as we go through these problems, so as not to take as much time. So we've got the integral of 1 over x squared plus square root of x squared plus 4. Now, I haven't been mentioning it before, but really you should try and look for other ways to do these kind of problems if you can first. U substitution would not work here because the x squared plus 4 on the underneath would not give us a way to easily get rid of the x squared on the outside of the denominator. Can't really separate this by partial fractions because these are not both polynomials, and don't really see any other way that we could probably do this problem. So again, we're going to go to Trig Sub. So our Trig Sub is going to be that x is going to be, in this case, you've got x squared plus 4, which is a tangent one, so it should be 2 tangent theta. Again, go back to the first page and you'll see that. We know we'll need dx, which is going to be 2 secant squared theta d theta. Alright, so we've got everything that we need now to go ahead and start our substitution. So we'll take the integral of 1 over squaring x to give me the x squared is going to be 4 tangent squared theta. I'm going to need a much longer fraction bar over the square root of 4 tangent squared theta plus 4, and then times dx, which is 2 secant squared theta d theta. Alright, doing a little simplification here of the square root underneath the fraction bar. Again, I'm going to try and do this without actually writing every step out. Now I've got this 4 in common right here. I can pull that 4 out of here, take the square root of it to the outside, so that'll be a 2. That would leave us with a tangent squared plus 1 on the underneath, so tangent squared, and then once you've pulled the 4 out, I'd have a 1 there. Tangent squared plus 1 is secant squared, so when I take the square root of that, I'm just going to have secant theta. And then here, on the top, I'm still going to have this 2 secant squared theta d theta. Alright, so let's see about what we can start getting rid of here. The 2's are going to go away. The secant on the bottom will get rid of one of the secants, so I'll get rid of that square. So what that's going to leave us with is the integral. See, I got that 4 on the bottom. Let's take the 1/4 out to the front. Oh, now I just got another thunderstorm warning. Great. So we're going to have secant theta over tangent squared theta d theta. Now these two things are related through Pythagorean identities. The tangent squared, again, is the same thing as secant squared minus 1. The problem is putting a secant squared minus 1 in the denominator here doesn't help us a whole heck of a lot. I mean, you can still do it. It's just going to take a lot more algebraic work here. So if I see something that looks like this, and I don't see an easy way to algebraically or trigonometrically manipulate this, I'm going to turn these both into terms of sine and cosine and see if I can work with that a little bit easier. So I'm going to change secant to 1 over cosine theta, and tangent is going to be sine squared theta over cosine squared theta d theta. Bringing the denominator up, flipping it over and multiplying as we do fractions would end up giving us 1/4 of, let's see, cosine squared would go on top, so that's going to eliminate the cosine in the bottom. So that's going to give me an integral of cosine theta. The sine squared will end up being in the bottom, d theta. Again, that's just doing fractional division. This doesn't look like it's much more helpful unless we split that up. And I mean, we can write that as 1 over sine theta times cosine theta over sine theta d theta. And hopefully what you'll recognize is that 1 over sine theta is cosecant theta, cosine over sine theta is cotangent theta, and this is something that we can easily take the antiderivative of because the antiderivative of that is going to be negative cosecant theta plus c. Now again, we did not start off in terms of theta, so we need to give ourselves a little right triangle. So we're going to go back up to the original trig sub, and I'm going to go ahead and take this, manipulate it, so that I can solve for tangent, which is x over 2. Tangent, of course, is opposite over adjacent, so that makes the opposite side x, the adjacent side 2. And again, it should not come as a surprise. The hypotenuse is going to be the square root of x squared plus 4. Using Pythagorean theorem, you can figure that out. So now I need, let's see, what do we need? We need cosecant of theta. Cosecant of theta is the reciprocal of sine. Sine is opposite over hypotenuse, so hypotenuse over opposite in this case is going to be square root of x squared plus 4 over x. So we should end up with negative 1/4 the square root of x squared plus 4 over x plus c. Okay, that one wasn't too bad overall. A little bit of manipulation here, going from the secants and tangents to the sines and cosines, and then knowing you can split that cosine over sine squared to be 1 over sine times cosine over sine. That gets us to a point where we can take an easy antiderivative. All right, moving along. Example number 4. X over square root of x squared plus 4. Well, that looks like it's the same form as the one we had from before. I've got an x squared plus 4. So your trig sub would be 2 tangent theta for x. That's what we could use. However, if you notice, x squared plus 4, the derivative would be 2x. I have an x on the top. It's going to get rid of that x on the top if I just use u sub. Oops. U sub is much easier. So u is going to be x squared plus 4. Du would be 2x dx. And dx is du over 2x. So now I can go ahead and integrate this thing. Integral of x over square root of u times du over 2x. The x's will go away, which is what we needed. I can pull out the 1/2 to the front. That would leave me with a 1 over the square root of u. I'm going to rewrite that as a power function, so that's u to the negative 1/2 power du. And in this case, the antiderivative excuse me, of u to the negative 1/2 is going to be, let's see, raise the power by 1, so that's u to the 1/2. Dividing by 1/2 is multiplying by 2. So we got 1/2 times 2 u to the 1/2 power plus c. The 1/2 and the 2 are going to go away, leaving me with just a square root of u. This was not originally in terms of u, so we'll go ahead and put in the x squared plus 4, and we get the square root of x squared plus 4 plus c. Much quicker and easier just to use a standard u substitution on that one. However, the trig substitution would have worked, and it would have gotten us to exactly the same place. All right, moving along. Number 5 is integral of dx over the square root of x squared minus a squared. Again, there's a specific reason why I have all of these in there. This is one that we haven't seen yet. Our trig sub is going to be that x has to equal a secant theta. And again, you can go back to the first page and see that that's the form that it's in. It's in the perfect form for that. So I know I'll need to get rid of the dx part. So that's going to be the derivative of secant theta, which is secant theta tangent theta d theta. So let's go ahead and make our substitutions. Dx is a secant theta tangent theta. The denominator will be the square root of x squared, which is a squared secant squared theta minus a squared. Alright, simplifying. Can't really do much with the top right now. The denominator, I've got this a squared here. Factor that out, take the square root out to the front, and we have an a. Leaving us with secant squared minus, well, you'll have 1 left over there. Secant squared minus 1 is tangent squared. Then you take the square root of tangent squared, and we are left with tangent theta. And I forgot my d theta up here, so we'll put that off to the side there. Hopefully you can see this is going to simplify really quickly. A goes away, tangent goes away. I am now simply left with the integral of secant theta d theta. Now this is not one that we're used to seeing. There's really no easy way to manipulate this one. It can be proved, but for right now I'm just going to go ahead and write down the antiderivative of secant theta. We did deal with this in the past, and I gave you guys a little sheet that had it on there. I don't expect you to memorize this one, but if you happen to, that's wonderful. The integral of secant theta is the natural log of the absolute value of secant theta plus tangent theta. So we're back to the point again where we've got secant theta and tangent theta. It didn't start off in terms of theta, it started off in terms of x, so let's go ahead and go back to that. Let's go ahead and draw ourselves our little right triangle. Didn't leave myself much room here. So I'm going to take and rearrange this one, solve it for secant theta. Well, that's actually kind of good because I need that. So I know part of this is the secant theta, which is x over a. I need to fill that stuff in to find the other piece of my tangent theta in here. So secant is the reciprocal of cosine. Cosine is adjacent over opposite, so this is going to be adjacent over hypotenuse. So secant is going to be hypotenuse over adjacent. So that means the hypotenuse is x, the adjacent is a. And again, it shouldn't come as a surprise. If you use Pythagorean theorem, you're going to end up with the square root of x squared minus a squared over there. And I need that because that's part of tangent. Tangent is opposite over adjacent. So we should end up with square root of x squared minus a squared over a plus c. Alright, we've got 2 more examples to do, 6 and 7. Those both are relatively lengthy because of the some of the trig identities and the algebra and stuff involved in there. So I'm going to come back with those in one final video.